Hello there, young students of chemistry. This is a quick recording about solutions and how solutions form. We're going to talk about how we measure concentration just based on the amount of solute dissolved, not with any actual numbers, some relative measurements. And then we're also going to talk about what happens when you put that something into water. What does dissolving really mean? So here we go. Solutions. The rule for solvation is like dissolves like. I'm sorry, I meant to tell you that you're going to be wanting to write these notes down. I'll tell you when they correspond with the papers that I've given you. But right now you need to write. So rule for solvation, like dissolves like. This means when we're talking about what is this like what? And it is like polarities. So what we mean is polar compounds will dissolve polar compounds, and nonpolar compounds will dissolve nonpolar compounds, but polar compounds will not dissolve nonpolar compounds. We discussed molecular polarity back in Unit 2 when we did bonding, and you guys came up with during lab that a good rule of thumb for determining whether a molecule is polar or nonpolar is if that molecule has lone pair. What we said is that if the bonds are polar, so there's an electron density shift between the two atoms, and the molecule structure has a lone pair on it, then we would predict that that molecule is a polar molecule. So this comes into play very heavily for solvation or the dissolving process. So we're going to talk about how ionic compounds dissolve, and we're going to talk about how covalent compounds dissolve. So we'll start with ionic. Ionic compounds are the most polar of all substances. Not only is there an electron density shift, but the electrons are actually transferred from one substance to another. We call the separation of an ionic compound in water dissociation. Another word for dissociation is dissolution. If you think about this, when you dissociate from a person, you remove yourself from them. You separate yourself from them. And that's exactly what's happening here. Here's a chemical or an equation to represent this process. This is a physical process. And you can see that we have solid sodium chloride turning into what we call dissociated sodium ions and chloride ions. Notice that the state symbol that I've put on those ions is aqueous. So for every one sodium chloride formula unit, we end up with 2 ions floating around in the water. So the ability of something, an ionic compound, to dissolve really depends on how strongly the ions are attracted to each other. We have looked at this before in Unit 2 when we did bonding. We looked at, okay, the relative solubility of ionic compounds. What we're going to do is multiply the charges together. And we said back in Unit 2, hey, if that charge is greater, then they're going to be less soluble. So as a reminder, if we look at sodium chloride, for example, the charge for each of those ions is 1. If we do the product of 1 times 1 is 1. Those ions are not very attracted to each other, and because of that, they can be more attracted to the polarity of the water molecule. So that is loosely what we call lattice energy. Lattice energy depends on charge product for us. So multiply those charges together. The higher the value, the less soluble the compound. So you can see there, more highly charged ions means they're more attracted to each other, less attracted to the water, and therefore less soluble. Now, water is a polar molecule. If you look at the dot structure for water, I'm just going to draw that up here really quickly. Water is H2O. This is what we would have done in Unit 2. And because it has a lone pair, we would have predicted that this molecule is polar. The electron density shift is away from the hydrogen and towards the oxygen. Because oxygen has a bigger nucleus, it's more attracted to any electrons that are in its vicinity. That is what we call electron affinity. So if you remember your periodic trends, oxygen has a higher electron affinity than water, and that makes this polar molecule. So what happens then is like this hydrogen region of the water molecule becomes charged partially with a positive state. The oxygen region of this molecule gets a partial negative charge. And it's not a true charge. There was no electron density transfer, but there is an electron density shift. So on this diagram, I'm representing chloride with a green circle and a green BB, and sodium with a purple BB. And you can see that when sodium enters water, the water basically rushes in and surrounds each ion. Because this is the positive ion of sodium, the negative portion of the dipole in the water surrounds the positive sodium ion. Because chlorine or chloride is negative, the positive portion of the dipole of the water completely surrounds that negative ion. And this is what a particle representation of dissociation looks like. When a covalent compound dissolves, these are a little different. Covalent compounds do get surrounded by water, but they do not dissociate. And this process is not called dissociation, it is called hydration. So we have a covalent compound that is polar, and that polar compound just becomes aqueous. This little equation here is how we would represent the hydration of a covalent compound. Notice we're not breaking anything up like we did with the dissociation. It's just a liquid turning into aqueous. So if this is carbon trihydride, or I don't know exactly what that is. I'm not sure that this was the best choice, but we can see what happens is that the water separates the molecule, but the molecule itself completely stays intact. So one molecule is separated from another. If this is a polar compound, the water is separating the dipole-dipole attraction that's occurring within the compounds. So covalent solvation, hydration, occurs when we have compounds that are dipole, meaning that they are polar, right? If their dot structure has a lone pair, or compounds that exhibit the hydrogen bonding attraction, which is really just a strong dipole force, if you remember that. So a little bit of review here. Good for you. Okay, let's talk specifically about gases. Because here's the thing, if we look at oxygen gas, oxygen has, its formula is O2. The bond is occurring between one oxygen atom and another oxygen atom. The dot structure looks like this. And the bonds are nonpolar because there is no difference in the electronegativity value of one oxygen to another. So if the bond is nonpolar, we would say, hey, this thing is not soluble in water. Same thing for carbon dioxide. The dot structure has two double bonds. There's no lone pair on the central atom. And if there's no pair, it's nonpolar. So this might be something that you're like, wait a minute. I know that in earth science or in biology, we talked about dissolved oxygen levels in rivers and streams and lakes because that's how the fishes breathe. They have gills that are able to take in any air that's dissolved in the water, and their body uses the oxygen much like our body uses the oxygen. So we do measure dissolved oxygen levels in water. So here's the thing, it's not a true solvation. When you have a gas that is nonpolar dissolving in water, the water molecules are actually trapping the gas in between them. There's really no interaction between the water molecule and the gas. So you can see here I've demonstrated oxygen with two red BBs and carbon dioxide with two red BBs and a black BB. So what happens is the water is really attracted to itself because it's hydrogen bonded. And if air gets in there, it gets trapped in the water because the water itself does not want to separate. So the water, in its attraction to itself, is trapping these gases in and among it. So while polar compounds and ionic compounds, when they dissolve, they're kind of stuffing the spaces in between the water molecules. But with gases, the water molecules are trapping the gas in there. This is why if you've ever had a fish tank, what do we put in our fish tanks? We put air stones, or sometimes they're like little like little pirate's chests, and like what and air like bubbles out of it and then goes through the water, because as those bubbles of air are going through the water, some of that gas is getting trapped by the water, and that is the dissolved oxygen level of your, mostly nitrogen, but what the fishes use is oxygen. That is the dissolved oxygen level of the water in your fish tank. So let's talk about how temperature affects the solubility of things. Temperature, it makes sense that if we're dissolving something that is polar or ionic, temperature is going to increase the space between the water molecules. So if we know we increase temperature, things are going to expand with thermal expansion. And this causes the solubility of a solid to increase as temperature goes up. And I say most solids. There's a little bit of thermodynamics going on in there that we don't have to really get to right now. But when you increase the temperature, you're increasing the space between the water molecules, and therefore you can stuff more solute into the solvent. Little vocabulary, hope you got that from your reading. Solute and solvent. However, if we're talking about the solubility of a gas, that gas is going to be less soluble, because if there's more space between the water molecules, there's going to be, it's like the gas can escape. It's like bars in a jail, right? If the bars were 3 feet wide, everyone would be out. But we make them narrow so people can't get through. It's the same thing with gases and water. If there's more space between the gas molecules due to the higher temperature, it's more likely that that gas is not going to stay dissolved. Gases are most soluble at high pressures and low temperatures. Pressure doesn't really affect the solubility of a solid, but for a gas, we have to pressurize that. And you know this because when you open up a can of soda pop, there is pressure inside that can. You feel the gas coming out of there as you relieve the pressure to equalize the pressure with the atmospheric pressure. So gases are most soluble at high pressures and low temperatures. We're going to talk in class about electrolytes. I think this is super fun, and this is a super fun little song. So we'll get back to that next time we see each other. Okay, so this is the stuff that corresponds with your note page that you have in your binder. There are 3 concentrations that we use outside of a numeric concentration, a measured concentration. We can say that a solution is unsaturated, saturated, or supersaturated. Let's rely on our understanding of prefixes. The word saturated, if you think about it, you think of saturated like saturated fat. That is a carbon compound that is filled with hydrogen. There's no double bonds. Every carbon has nothing but hydrogen on it. A saturated sponge that is filled with water. So saturated means full. And when we're talking about a solution, what that means is that we cannot dissolve any more solute. without changing the temperature. Solute is the stuff we're dissolving. Solvent is the stuff doing the dissolving. So knowing that saturated is full, the prefix un means not, right? So, or below. So this is below saturated. It is not full. If we put more solute in, that solute is going to dissolve. So here you can dissolve more solute without increasing the temperature. Super as a prefix, if you think about the prefix super, we've got Superman. Superman is a man above man. So super means above. So this means that this has more solute dissolved than theoretically possible. Not all substances will supersaturate. Probably the most common thing that you're familiar with that supersaturates pretty easily is sugar and water. If you've ever made rock candy, what you have done is created a supersaturated solution of water and sugar, and then if you let that cool very slowly, all of the extra solute that's in there starts coming out of solution and forming these crystals, and we call that rock candy. So we've got saturated, unsaturated, and supersaturated solutions. Now this diagram is what we call a solubility curve. The line on the diagram represents a saturated solution. So if we consider the solubility curve, let's say here for sodium nitrate, which is this line here, any point that lies above the solubility curve represents a supersaturated solution. Any point that lies below the solubility curve represents an unsaturated solution. And then any point that lies on the curve represents a saturated solution. So we can use this to determine how much stuff can dissolve at different temperatures. So let's answer a couple of questions about the solubility curve. We can see that this says how many grams of potassium bromide will dissolve in 100 milliliters of water at 80 degrees Celsius. What's important for you to look at is that they're asking about 100 milliliters of water. You need to look at the label on the axis of your graph. This graph happens to be in grams of solute per 100 grams of water. And remember that 100 grams of water is 100 milliliters. So what are we going to do here? We're going to find the temperature 80 degrees Celsius, and we're going to find the saturation line for potassium bromide, which is right here. So if we follow that 80 up to the potassium bromide line, there's the point on the line. That point represents a saturated solution. So now we're going to read that, we're going to read that point over. And if you look really closely, it's just a little bit less than 100. I would probably take answers anywhere from 95 to 100 on that. But it would be, I'm just going to go ahead and say 100 grams of potassium bromide are able to dissolve in 100 milliliters of water at 80 degrees Celsius. Let's look at the next question. It says, how many grams of sodium nitrate will dissolve in 500 milliliters of water at 10 degrees Celsius? So we're going to find 10 degrees Celsius. We are going to look for the sodium nitrate curve that's way up here. And we're going to follow that 10 degrees up. Boy, that's right at an intersection. That's nice. It's clear that we can dissolve 80 grams of sodium nitrate. But be careful, because remember that this solubility curve is 80 grams per 100 milliliters of water. We have 500 milliliters of water, that we're dissolving this into. So what we're going to have to do, we have 80 grams per 100 grams of water. So how much for 500 grams of water? Right? So, oh, I don't want to do it like that. That'll work. So it's really like 80 times 5. What is that? 80 times 5 is 400 grams. I better double check that. You know how my math skills are so terrible. Yeah, 400. I don't necessarily need to see your conversion factor, but know that you've got to multiply that value by 5 because it's 5 times as much water. So the next question says, which salt is most soluble at 40 degrees Celsius? So the salt that's going to be most soluble is the one that's going to have the most solute in it, the highest concentration, right? So we're going to go to 40 degrees Celsius and we're going to follow that up. We can see that the least soluble salt is sodium chloride here, and then we get more and more soluble until we get up here, and that's the most soluble salt. Follow that line to its substance, and that is sodium nitrate. Let's use our words where we can. Okay, when 100 grams of bromine are dissolved, or potassium bromide are dissolved in 100 milliliters of water at 60 degrees Celsius, what type of solution is formed? So to answer these questions, we're simply going to find that spot on the solubility curve, and then we're going to look to see where does it fall. Is it on the line, above the line for supersaturation, or below the line for unsaturated? So we've got 100 grams at 60 degrees Celsius. So here's 60 degrees Celsius. Follow that up to 100 grams. Whoops. There's the point. And we want the line for potassium bromide, which is here. We can see that that point clearly lies above the potassium bromide line. So this solution is super saturated. Here's another of a similar question. What type of compound do we get, or solution do we get when 80 grams of sodium nitrate are dissolved at 10 degrees Celsius? So we are going to find 10 degrees Celsius, follow that up to 80 grams right here. There's the point where the two intersect, and we're going to find the line for sodium nitrate. The solubility curve for sodium nitrate is this curve here. So we can see that that is right on the line. So we would say that this solution is saturated. For which salt is solubility least affected by change in temperature? So what we're looking at here is the salt that has the slope that's closest to 0. So if we look here, the flattest line is clearly the sodium chloride line. That barely goes up as you change temperature, which is a good thing because we wouldn't want the salinity of our oceans to change when the seasons change, right? The animals that live in the ocean, they need a specific salinity to survive. And if they don't have it, they will die. So sodium chloride changes the least. And if we look at our graph to answer the last question, what is the relationship between solubility and temperature for most of the salts that are present here? And if we look at that, we can see that for most of these salts, as temperature increases, solubility increases as well. So that, of course, would be a direct relationship. Increased temperature, increased solubility. So concentrations go up at higher temperatures. Okay, so what you should do now is your problem set 1. It is on a solubility curve. You will see probably a different solubility curve on your paper, and you can answer those questions. Thanks.